some rain where you are. I'm Phil Brink with Colorado Cattlemen's. I'm the consulting coordinator of the Ag Water Network. I am joined by Sarah. Sarah Didrikson is in the background. She helps to keep things running smoothly. And today we are going to be talking with AJ Brown of Colorado State University about salinity in soil and water. So AJ is going to be talking about what salinity is, how it can affect crops and forage, and practices to help manage it. AJ is a data scientist with Colorado State University's Ag Water Quality Program. He has a master's degree in crop science, and he is a certified crop advisor. He grew up in southeastern Colorado in the lower Arkansas River Valley, and so he worked on a farm there that had salinity impacted soils. I'm guessing that's probably what influenced him to get interested in salinity. He also focused on salinity here in Colorado and Pakistan during his graduate work, and then afterward, now he's a researcher for the Ag Water Quality Program. AJ, do you want to go ahead and see if you can share your screen?
Will do. Thanks for that introduction, Phil.
Yeah, so just a reminder, today's webinar is being recorded. We will post that on our website at agwaternetwork.org later, along with highlights of the webinar. So, AJ, unfortunately, salinity does not seem to be an issue that's going away anytime soon. And in fact, looking at the data, it seems to be expanding worldwide in terms of the problems associated with salinity. So it's something that we need to figure out as best we can here in Colorado, dealing with salinity and how we can continue to produce crops and forage and be productive, and even maybe bring back marginal lands that have lost some productivity. So eager to hear you talk about that. And then one more thing, we will hopefully have a few minutes at the end for questions. So if you got those, just hold on to those and we'll try to address those at the end. So AJ, whenever you're ready, you can start rolling.
Absolutely. Before I begin, Phil, are you seeing my screen, and is everybody seeing my screen?
Yes.
Excellent. Thank you so much. Great, Phil. Yes, I think salinity is my soapbox of the day. And we know we all wear many hats, but salinity is one that's kind of near and dear to my heart because, like you said, growing up in Rocky Ford, Colorado, in the Arkansas River Basin, it's an issue that affects us more and more every day. And it's not a problem that you see in your lifetime usually, but maybe your grandkids' kids really have to suffer from decisions you make today. So without further ado, I'll jump right in. So a little background on myself. I think some of the names I've been seeing on this call, I might have met you before, but if you haven't met you yet, I look forward to it. My name is AJ Brown. Like Phil said, I'm a certified crop advisor. I'm an ag data scientist by trade, but that's after a few different career paths and changes. But my research initially started with looking at soil salinity, both in Colorado and in Pakistan, because what causes soil salinity? A few things, but one of them is irrigation practices, right? And so they're always intertwined. And this, in the southeast area of Colorado, where I grew up in Rocky Ford, has been under intensive irrigation for a long time because it was the first part of Colorado that was settled by the East, by the Europeans. And so since then, they've been trying to farm it. And so we're starting to see the impacts of salinity since then, right? 250, 300 years ago, we're starting to see it heavily now, but that's how long it takes. So today we're going to talk about a lot of the things that we can do about it, where it comes from, and what it does, so that we know why it's important and why we need to think about it now instead of later. So I like to take everyone back to an initial kind of chemistry lesson, and not too deep. Don't worry. It's just to understand what a salt is, right? So a salt, it's not just table salt. It's not the stuff that we put on our beef for dinner, right? It's just a chemical compound that's comprised of a positive and a negative charged. So table salt is a salt, sodium chloride, but it's not the only kind of salt. The sodium is the positive, the chloride is the negative. And the other unique part about salts is that when you put it in water, it dissolves. And when it's dissolved, it's able to conduct electricity. So those are kind of like the things that we need to keep in mind as we go forward about, well, what is a salt as opposed to something else? Like, syrup isn't a salt. It might have salts in it, but it's not a salt. And so that's why I put up this slide here. So sugar is not a salt. It dissolves, but it doesn't conduct electricity. These are just some chemical properties to keep it in mind. But for example, a lot of fertilizers are directly salts, like nitrogen, nitrate, for example. Great salt. And I also like to plug in here and say electrolytes. That's what that is. So salt is an electrolyte. That means it conducts when it dissolves. When you're drinking your Gatorade, it's just full, and they say it's packed full of electrolytes. Just know you're really just paying for salt. That's all it is. And so why do we care about these salts? Like they have these unique properties, but what's the deal? What's the problem? Well, this map, it might be a little hard to see, but the parts you can see are the important parts. It's an outline of the world. It's a map of the entire world. And any part that you can see color that's not gray or white is an area that we estimate to lose productivity because of overaccumulation of salts in our soil. And it's just free money going down the drain because we've mismanaged that land. And you think about the historical perspective, if you've ever heard of or seen of the ancient gardens of Babylon and the Fertile Crescent, in the Middle East, that started as one of the most fertile areas on historical record, but it's degraded over time because of intensive irrigation and mismanagement and salt accumulation. And eventually it became a desert because of salt. So the same effect is happening everywhere. And we lose a lot of money globally for it. And here in the United States, the arid West, i.e., Colorado, is a big area where we need to be concerned about this accumulation and management of salts. And so then the next question is, okay, if they are accumulating everywhere, where do they come from so we can manage it? And so this is a picture of one of my research fields in Rocky Ford, actually, where you can kind of see some of the salts accumulating at the surface. Very kind of cool because it was a very salty field. Not great for the farmer we were working with, but I've never quite seen it like that before. It was pretty concentrated. Salts, I guess technically, the origin of them is always geology, right? It's raw minerals that erode from other things, and then they come and into other pathways through wind and water and all kinds of physical destruction and all of this stuff, and gets broken up. But also the main influencers of that are things like climate. Anytime your evaporation exceeds your precipitation, you're going to be left with salt. So it's kind of like when you have salty water and you boil it off, the salt is left. Same kind of thing is happening in your soil. Every time we reuse water, so it's a hot topic in urban water right now, is gray water reuse. Well, guess what the biggest pollutant in that is it's not really like the stuff that's running off like chemical wise. It's your salts. If you reuse it so much, you get too much salt, and you're gonna start burning things up like your lawn, which aren't very uh, robust against those kind of things. So it's a major concern in gray water reuse. Human activity, of course, things like manure, fertilizer, de-icing, wastewater treatment plants, oil and gas, brines, urban runoff, all have a lot of salt in them. And so those are things that where we get to control what we do. And then the water table as well. I'm going to harp on this a few times in this lecture today, but water determines where the salt goes. And so if you have a shallow water table or poor drainage or like a soppy area, a swamp, you're just creating salt problems just by having the water not being able to go anywhere. So if you think about it in simple terms, this 101 that I put over here is that all water basically has salt in it, and to some extent, even rainwater. But salt will only accumulate where the evaporation and transpiration exceeds the amount that we add, right? So that can also include irrigation. So if we use more water than we put in, then we'll be left with the salts, just like boiling it off. And then finally, the drainage part, if the water has nowhere to go that contains the salts dissolved in it, then it's going to stick around and it's going to accumulate. And here's a better way to talk about it. So I verbally explain it, but this little graph that I make really shows it a lot more simply. So, let's say we have a field, we have some crops in it. And, when I put water on through an irrigation event, for example, I'm putting some salts there. When I put fertilizer on, I put some salts there. When I put manure on, I put some salts there, or compost. Some of the water runs off if I'm irrigating, let's say a flood or whatever, wild flood. Some of it will run off, but not always. Um, and then if I have this water table, for example, it can also bring up salts from the bedrock. If the, well, a lot of the fields I've worked in before have shallow water tables, and so every time that table rises and then dries out a little bit and goes down, it leaves a little salt every time with it. So you get this accumulation or this salt sandwich in your root zone that really becomes a problem. And so if you can imagine this on many fields, right? So a whole watershed, and we're trying to manage that. You could have a cornfield, a wheat field, and a grazing field. They're all contributing salts in various capacities, or maybe they're not contributing. Maybe they're suffering from the work of their neighbor, right? So these are all the questions where it's really hard to figure out, but it's going to be critical especially in areas where it's just starting to pop up, like the South Platte. We've been looking at salinity, but now in the more recent years, it's starting to become a problem. Whereas in the Arkansas basin, it's been a problem for a while. So, you know, how do we measure it? These are the questions that we need to ask. So, perfect timing. How do we measure it? What does it look like? Well, salt, going back to what it is, right? It conducts electricity when dissolved in water, and that's by far the biggest way that we try to measure it. So if you take a soil sample and send it off to a lab, what they will usually give you is some sort of what we call a paste extract. And so here on this picture we have the what I call the gold standard. That's a saturated paste. It's just enough water. It's like a Dairy Queen cup. It needs to stay in the cup when you flip it over, but also be or you get it for free, but there's other kinds too. And that the saturation extract is not the one that's most often used, but it's what we've based a lot of our literature on as far as understanding what it does to plants and other things. So, but it is a lot just mixing that soil with water and then sucking it out. So these mixtures of mud are placed into a vacuum that suck out the water, and then we put a probe in that water, and then we measure what we call the electrical conductivity, and that is our proxy for how much salt is in that soil. And so you have poor water EC if you suck it out directly in the field with like a suction, what we call a suction lysimeter. Don't worry about that. You'll probably never encounter that. Applied water, so the water that's going onto your field, you can stick an EC probe in that. That's important, ECW. Saturation extract, that's what I just talked about. And then we have these gravimetric extracts. That's a little more simple than a saturated extract. That's just either, for example, the EC 1:1 I show here, that's equal parts soil and water by weight. But then there's also the 1:5. So it's 1 part soil, 5 parts water. So there's a couple ways that people have done it over the years in all various capacities. But that's why it's also important to understand all these ways, because if a lab reports you something, you need to know which one of these it is. And then the other way you'll see it, and this is more important for water resource managers because they do things like calculate total loads and what's allowable in the river and all this kind of stuff. But total dissolved solids is the amount of dried, it's the salts left after you boil the water off. That's the dissolved amount of solids, and that's purely the salts. So that's what you get out of the lab, and you can kind of see here's some ways that we do it. And when you ask like, well, what are they doing in the lab? At the top we have these things called EC sensors. It's just a magic wand we stick into water, and then it gives us this conductivity reading. It corrects for things like temperature and all this other stuff. We can talk about that if you're interested, but that's pretty simple. There's these other types of device called spectrometers. Very fancy. There's a lot of different kinds of ways. They're like $100,000 instruments. You vaporize the water and you look at, there's different ways, but you find every ion in the water, whether that be a sodium, a chloride, a calcium, whatever. And then you add all those together. That's TDS. And then you can actually just filter the water out and boil it off. And that's like also a very true way to get TDS. And so depending on what you ask for from your lab, these are the things that they're going to be working with. But just to reemphasize, because the lab can do so many things, it's important to know what you're getting back. And most often, labs will give you back what's called the EC 1:1 and not ECE. ECE is the saturated paste extract, which we base all of our literature on for crop yield reduction, for example. And so it's probably the more important number. But most often people do EC 1:1 because it's just easier to make. It's just equal parts soil and water, super quick, super simple. So if you are trying to do like an economic model or estimate your yield loss efficiently, there are ways you can calibrate ECE to one based, like you'll have to do it on a per field basis. But the easier way is just to make sure when you send that soil off to your lab, ask them to do saturated paste instead of EC 1:1. And, you know, it might cost a little extra, but not much. Um, the other thing I'll caution you is like most salts aren't usually found at the surface in Colorado soils. Most salts are a little deeper, at least in the irrigated soils. Maybe in a dry land or pasture setting, you'll find them at the top. But in irrigated fields, they tend to be accumulating near the bottom of the root zone because the water that we apply to the field pushes them down when they dissolve. But in the rangelands, the evaporation brings all the water up. So then you'll see a lot of accumulation at the top. So just keep that in mind when you soil sample, because if you're trying to figure out where your salt is and what you need to worry about for a crop, you need to sample for the whole root zone. That's the idea. So that's not the common just top foot sample. You need to do a little deeper to figure that out. Or in a rangeland, you know, maybe the top 2 feet is plenty because most grasses or whatever will be there. It really depends on your root zone is how I would define it. But if all you have is EC 1:1 and you really just don't have any way to get ECE, the rule of thumb is to multiply it by 3, but it can vary between 1 and 3. So you may want to do some extra calculations to see what if it was actually 1 to 3, like you multiply it, right? Or divide. So if I had an EC 1:1 of 1, my ECE would be 3. Sounds good. There's ways, and this is if you're wondering like, well, how do I get this over my field? There's a lot of different ways, and you probably won't need to do this often. If you're interested in this kind of work, just reach out to me. But briefly, I'll just go over and say there's devices that we can use to walk over our fields, like in the top left here. This is one of my students from Pakistan. She came over and we taught her how to use this device that maps the salinity in a field by shooting electricity into the ground. There are also soil moisture sensors that measure EC at a certain spot over time. Pretty valuable if you're needing to understand if I'm leaching them out or where the salt's going. There's also been experimental ways to look at satellite derived ways to do it, but it's pretty hard. So I wouldn't rely on that or be investigating that much in a practical sense at the moment, but it's an active area where people are really trying to pursue. And then you have the old traditional soil sampling regime where you take a sample, like one random sample per acre grid, and then try to put it all in a map, which is pretty intense. So I don't recommend that much either. So as I mentioned before, there's a lot of different kinds of salt. It's not just table salt, and we don't have to, this is mostly here for your reference, and I'd be happy to send out this PowerPoint at the end of the presentation today, but just to show you, it's not just table salt. There's sodium sulfate, there's, you know, magnesium, there's calcium, there's nitrate, there's all kinds of stuff going on that can cause this salt issue that you see. So, you know, if it's a white salt, that's one thing. If it's a black salt, that's another. So it's not as simple as saying, I just got one type of salt. Let's do something about it. And salts impact the soil, the water, and our plants differently. And so today I'm just going to talk about why we, you know, what does it do to the environment that we need to be concerned about and make sure that we prevent. So firstly, our soil. There's two main classifications. There's actually three, but we we categorize them by the type of salt that's in the soil. So on the left, I have this picture. It's called sodic soils. That means think sodium. So sodium's so bad that we give it its own category. So if you have a sodic soil, it's dominated by the sodium cation. And so you get loss of structure, reduced infiltration, worse erosion, and you get this black powdery residue on the surface. And so that in that bottom left there, I see a soybean. Actually, it's a dry bean popping up, and it's got a lot of crusting there. On the right side, we have everything else that's not sodium, and it's just generically classified as saline. And oftentimes you'll see this appear as like white crystals or white powder on the top of your soil, like in the other picture that you saw of me walking through that field. In this case, it's kind of the hidden killer because it's still bad when it accumulates too much, but it actually improves your soil quality up to a point. You'll get better infiltration, better aggregation, better you'll get higher pH, which isn't always good, but it's certainly not the end of the world. So it can be a problem later down the road. But luckily in Colorado, we see a lot more alkali and saline soils than we do sodic. However, sometimes you can have both, and that's called a saline sodic soil. Very original naming. Us scientists are very good at naming stuff. Um, and the worst case scenario, because we'll talk about how you manage that next. But um, once again, this is a slide where it's mostly reference section, so I'm going to point us towards this image here. Why is sodium so special as opposed to everything else? Well, some chemistry about sodium is that it has a positive charge, but it's only got a +1 charge. And so that means once it has a -1 charge and just one negative, it's happy. It's balanced. Thermodynamics are very pleased at that point. Calcium and other salts like magnesium, on the other hand, have a 2 positive charge, 2 plus. So if it has a -1 charge, it still has room to hold another hand. I call it holding hands with the soil, because soil has an overall negative charge for the most part. And that's when if you're familiar with soil testing, you have what's called the cation exchange capacity. That's the amount of positive charges that the soil can hold. And when you have a calcium that can hold two hands, it actually brings two soil pieces together. Whereas the sodium, it will hold one hand and then it's just going to be happy. And so when that happens, all the soil starts coming apart into what we call dispersing, because now it doesn't need to hold on to itself. It's got that one piece of sodium and it's just going to become a little dust particle all on its own. So that's why it's so detrimental, and that's why sodium gets its own category, because it can really, the symptoms are totally different and it's a lot worse. And I guess back to the slide really quick. SAR, this equation here, you'll see that reported by labs often too. That's the sodium adsorption ratio. So that's the ratio of sodium to the calcium and magnesium. And so the higher that is, the more sodium you have relative to the other, which is telling you if you have a sodic soil or a saline soil. And it's important for management. That can happen, and we'll calculate that for soils and waters. So now water. The water part is pretty short, but it's pretty impactful. Salts themselves can harm waterways, just because drinking too much salt is bad for you, just like we can't drink ocean water. But it's actually way worse in its what I call secondary effects, and that we get this cocktail of pollution when you put salt into a water system. What can happen is that all of these other chemicals that we normally wouldn't worry about because they're in a form that's not dissolvable, it can't get into the water, it's just really happy where it is. If you put salt into that system, it now changes the thermodynamics so that all these other things like, the iron, the barium, and all this, selenium, it all now says, well, I would love to be in the water. That would be lovely because the salt took my place. So now it's very cool for me to be in water at the moment. And so when you introduce salt into the system, all of a sudden you can start seeing spikes in things like trace metals, nutrients, organic matter, and other major ions into your river that weren't even there before, because now the thermodynamics have changed in the system. And so that can really damage infrastructure. It can cause human harm with things like, lead pipes and other things like that. And it can just, cause reservoir damage and other things. It's a terrible thing for water resource management. So the best strategy is to avoid putting it in the water in the first place and keeping it in the soil. But along with that, how do I know if I have a salt problem in my water? Here's an example meter that you can get on Amazon in the bottom left here for about $35 to $75. And it gives you that electrical conductivity. And I would highly recommend buying one of those, because putting that in your inflow water is the best way to help figure out how much we need to apply to fix salt problems later. But this is a table, once again, mostly for reference, but it shows you if you have this meter, whatever your reading is, this will help you figure out if your water is good to use or not. Addition to the EC, I talked about this SAR. The better way is to have both the EC from your cheap sensor there and also the SAR from a water test in a lab. Shout out to Spur in Denver if you want to get your water tested. they can report the EC and the SAR for you. And this is really the more intelligent way to figure out if you have good water, because it accounts for the fact if I have sodium or magnesium or calcium better. And so you can avoid making your problem worse that way. And just a brief little plug, if you need to take a water sample, use a plastic bottle, rinse it 3 times with that water, screw the cap on tightly and refrigerate it until you ship it, and try to ship it overnight or drive it there day of to give it to the lab. Arrange for that. And then for salts, we actually have a long time, but you need to get it there within 28 days of taking your sample. So get in touch with me if you need more help on best practices for sample collection. So now we want to talk about the crops. This is what what most people care about, it seems, because this is where the economics come in a little bit. But so here's a picture from some of my research where I looked at cornfields in Rocky Ford. And on the top picture, we had a corn cob from a high salt zone and a corn cob from a low salt zone. Beneath that is a picture of the corn where that high salt zone was. One thing I like to highlight here is that picture. It looks like really dry, drought-stricken corn. But I can tell you, it had sufficient water the entire season. It had a water table, it had regular irrigation, it wasn't waterlogged. I mean, it just had so much salt. And so why does it look drought stricken? I'll show you why next. But how do I know if I have a salt problem? It looks like drought stress often. But you can also see things like yellowing of your leaves and leaf burn, and you can also see things like nitrogen deficiency and other nutrients that may normally be there but aren't, because the salt ions actually just get in the way in the roots and prevent the other normal nutrients from coming up in the plant. And this reduces yield, it reduces ET, it causes plant death, all kinds of bad things, right? So let's zoom into that drought stress feature a little bit. Why does the corn, or why does your crop look drought stressed when you have too much salt? Well, I hate to take it always back to the high level like thermodynamics, but I have to here again, because the way plants uptake water is through energy. And this energy is really just how dry something is. And so I like to show this picture here on the right where the air is the driest. And we actually measure it with suction. It's PSI, pounds per square inch, just like your tire in your car or in your bike, right? So the air is the driest, the leaves are the next driest, then the roots, and then the soil. If that pathway is not correct in that way, if that's not the order of dryness, it won't work. And that's how you get drought stress. And so even without salts, that's the same thing. If your soil's drier than your roots, then or if your roots are drier than your soil, it's not going to work. So here on the bottom, I put an example of a soil that had an EC 1:1 of 1. -4 psi is more positive than -44. So we're good. Even if we double that salinity and do an EC 1:1 of 2, we had a -22 psi, which was still good because the roots were -44 psi of suction. So the roots still overpowered the soil. But finally, if we double it again and had an EC of 4 and we have -46 psi, it doesn't work anymore. That water chain of suction is broken because now the soil is sucking onto the water more than the roots can suck onto the water. And so therefore, drought stress happens. And that's what salts do. Salts being in the water create an energy imbalance that prevent the water from being uptaken. So this is usually the #1 stress symptom that we see in Colorado, followed by nutrient toxicity, so the yellowing and all that kind of salt burn type situations. And so there's been a lot of work on this. This is a concept that's been studied for a long time because salinity is like a global issue that's like
my lap. Oh,
it's the #2 threat to security after erosion. And so here's an example of what some researchers have done over the years to figure out, when I have salinity, what is my yield supposed to look like, or what should I expect? And so I have this little chart that shows, the root zone salinity on the bottom, and then you have what's called relative yield from 0 to 100%, 100% being you have no yield loss relative to normal amounts, and then 0 meaning, plant death. So corn and potato are relatively sensitive here. That's the blue and the black dotted line in the near part here. So it doesn't take much salt to start losing yield to corn, which is unfortunate because we grow a lot of corn here in the United States. The next thing would be alfalfa that I show here. Winter wheat is a little more tolerant than that. And then barley is even more tolerant than that. But there's like hundreds of crops that this relationship has been made for. So you can go find that information pretty easily and I can point you toward it. And then, so you would take a map like this, for example, if you're able to create a map from a few soil samples or from this meter that I showed you earlier, you basically just convert the EC and put it in this equation, and then you estimate what your yield is going to be relative to 100% of what you expect. And that's how you can estimate what your yield is going to be out of that field. And then you can decide, is it worth planting that crop or a different crop? Or there's other options, right? So, but that's kind of the strategy. And so management strategies, instead of just looking at the economics and just how much yield I'm going to lose, there's a couple things that we can do to kind of control the salt in our field, hopefully. And they revolve around two main principles. What can I do in the soil, or what can I do with my crop? And so generically, it's all about water movement. So the soil-centric methods, by far the number one most recommended way to deal with salts is leaching. And so this just simply means I'm going to irrigate extra either during the season or before or after the growing season to flush out the salts out of the root zone. And then the plants don't have to worry about it. There's also tile drainage. That's pretty extreme and not often economical, but in some cases, it really is. It is economical to install these tile drains that keep the water table out of the way, as well as it gives the salt somewhere to go outside the bottom of the root zone. It just depends what your crop is, what the productivity per acre is, and you have to figure out the cost per acre of that drainage tile too. But it can be profitable, and it has been profitable in areas like Yuma, Colorado, where the corn yield is so high that if you start losing that yield because of salt, putting in that drainage tile was pretty no-brainer to get it back up to 300 bushels per acre, right? It makes a lot of sense. And then finally, there's other chemical amendments, but I put it last intentionally because going to chemicals to fix a chemical problem is not often the go-to. It's kind of like we should figure out what the cause is first and work from that instead of just trying to fix it with magic chemicals, because that's not often going to be your solution. If you have a sodic soil, you can apply gypsum to that. It's funny, the gypsum will replace the salt or the sodium in the soil, and then it allows the sodium to leach out next time you irrigate. And if you have a carbonate soil, so calcium carbonate is another big salt in Colorado, and if you have too much of that, you can put sulfur on it, and that will kind of free up some of that for leaching. But that's not as often as big of a problem. And then, okay, so the crop-centric methods, I kind of talked about this already. So the first real method is switching to a more tolerant crop. If you are seeing salt damage from corn, switch to wheat. If you're still seeing it, go switch to barley, these kind of things. And so weigh the pros and cons of that. This other method, probably not really my go-to, but it's possible. And basically the idea is like afforestation, that is taking your fields out of production for a while and just letting it habitate with like natural species and kind of become a natural area for a minute, and then taking it back into crop production. That will really help too, because really what you're doing there is you're allowing the roots to create leaching pathways to reestablish that clean root zone and getting the salts out of there. So if you're not interested in having that field for a while, this is an option that you could consider. And here's a reference table for you guys to kind of see, what are salt tolerant crops versus what are not. Sensitive crops generically tend to be your more vegetable-y type crops, things like, peaches, oranges, avocados, carrots. Those are all very salt sensitive. Strawberries are very sensitive. Then you start moving your way towards the tolerant stuff, which are like barley, Bermuda grass, cotton, wheatgrass, tall wheatgrass, stuff like that. In this particular thing, I highlighted or I bolded ones that are kind of applicable to livestock producers the most. I would think like forages like alfalfa and stuff, definitely a lot more relevant here. But and triticale is also in that moderately tolerant. I didn't list it here, but it's a moderately tolerant crop, and I'd recommend it. And so there you go. That's kind of, there's even more than this. This is just a table for reference, but there's even more than this. And so if you're interested in the nitty gritty or trying to actually do some of the math on this, you don't have to start from scratch. You can scan this little QR code, and I can come back to it at the end if we need to, but I built a little Excel tool that lets you say, okay, here's my soil result. How much water do I need to apply? Or how much yield do I expect to lose? And that kind of stuff. So if you want to try it out, give me feedback. I'm always looking to try to make it better too. Go ahead and download that Excel tool and let me know what you think. So finally, the bonus today. Normally I speak with crop producers, but today I'm speaking with the Colorado Cattlemen's Association. And so I wanted to definitely put in some comments about livestock and grazing. So first off, I would say generically, the salt problems are vastly due to overgrazing rather than correct grazing. Proper grazing, good grazing management is not going to usually result in salt issues. So I wanted to talk specifically about right off the bat. If you overgraze, what are the things that you might see specifically related to salt? So when you continuous graze, you start getting compaction, reduced infiltration, more runoff, and all of those things, the messing with the drainage pathways, that will tend to increase or exacerbate your salt problems and leave the salts more in the field. And then so grazing can also increase the evaporation rates, right? So if you leave a lot of bare soil, the desertification happening, overgrazing leads to more and more bare soil, and the more evaporation that's happening, once again, if you don't add enough water, what comes to the surface? Salts. It's going to bring it up with it from the soil. And so you're going to start seeing salt impacts at the surface. And then finally, for those who use manure application, a lot of the crop producers and also rangeland people, manure is really big and heavy in salt, and so is compost. And composting it doesn't make it better because the salts don't really leave. It still stays moist. It's in fact probably concentrated in compost. So when you get your compost test or manure test, be aware of that salinity issue and make sure that after you apply it, or after, if you're doing like a 3-year regime to see what's going on and improve your soil health, make sure you keep an eye on that salinity and make sure that your nitrogen and phosphorus bonuses aren't offset by your increase of salinity, because then you might want to consider switching to a more chemical type fertilizer than a manure, because it's a little more complicated than that. So now let's talk about what the salts themselves can do to your livestock. And it's kind of, the direct impacts would be things like water quality. So if your water becomes too salty, it's really bad for them. It's like we said, we can't drink salt water, neither can they. It's like the reason why you're thirsty after eating a potato chip. It's that water is being competed for by the salts in it. And so salty water and that chemical cocktail situation that I talked about can really be a concern in grazing systems and other things like that. The other thing to be aware of is the forage quality is obviously going to go down. Not only will your tonnage decrease, but the protein is going to go down, your palatability is going to go down, you're going to see more lignin-y type materials. It's just not all around good. So the indirect impacts, though, are that your soil structure will decrease in the sodic soils, the erosion will increase as well. And so that increases desertification and all this evaporation problems. And then kind of an interesting one to think about is just the natural process of selection. The salt tolerant plants will be the success when you start accumulating salts. Your composition will start shifting towards salt tolerant species, which aren't always the most palatable. Not saying they aren't, but just keep an eye on that, because the reason why your composition could be changing is because of salt tolerance. And then just some best management practices, right, is keep using that rotational grazing to allow the soil to stay healthy, because if you keep that soil healthy, there will be natural pathways to keep that salt out of the root zone and out of the problem. Grazing exclusion, if there's areas that you can give a rest for a while, that's going to be good. Maintain vegetative cover. I know the evapotranspiration will still suck it up, but it's just definitely better to keep those living roots in the soil that can uptake the salts and also keep those pathways for drainage open. And then soil amendments. It's the same as the cropping systems. Consider the gypsum, consider the sulfur, whatever you need. And then drainage. If the water has nowhere to go, the salts will stick around. That's all there is to it. With that, I think I'm gonna wrap up. So we're about 40 minutes. That's great. That's perfect timing for what I envisioned today. And I'll turn it over for the audience for any questions or if Phil has any comments. So thank you for your time today, and I really appreciate it. Thanks for letting me be here.
Yeah, great job, AJ. That's a lot to absorb. So I'll just start out with a question here. And if you have a question again, yeah, go ahead and throw it in the chat if you want, or you can just unmute yourself and just ask the question. So there's a lot of emphasis right now on soil health. So can you reduce your salts? Can you grow more, let's say, more salt intolerant crops by improving your soil health, by increasing your organic matter, or does it matter?
Yeah, great question, Phil, especially since soil health is a big national initiative right now. And I mean, everybody's asking, soil health, soil health, soil health, what can I do with it, right? In this case, I would just say that soil health should also be a function of salinity. I mean, increasing your organic matter is always good. How it would affect salt would simply mostly be due to increased water holding capacity. So if your soil can hold more water, when you irrigate, that means the salts will be more dilute. And so the impact on your crops will be lessened because there's more water to keep that salt from being a problem. But when it's a little drier, that salt is a lot more potent, if you will, and it can hurt things a lot worse. So, but that being said, I wouldn't recommend it as like that's my go-to to fix your issue, but it is a go-to to say if you want to avoid salt problems in the long run, it's a great goal to increase your organic matter and try to keep that plant available water and that water holding capacity high. So does that answer your question, Phil?
Yeah.
Great.
TW, you've got a question.
Yeah, thanks, Phil. Mine's a multi-part question of public policy, infrastructure, and technology.
Sure.
So up here in extreme northwest Colorado, we're in the ancient Pleistocene sea beds, and I've been told in the past. I mean, we're all talking about soil health, and I love the part where you had all about drainage. But I've been told in the past, from public policy standpoint, NRCS will not cost share on tiling and drainage. Has there been any change, Phil, in that issue? Because if we don't have some help to be able to move this salt, our long-term sustainability is at issue. And then I've got the other parts of this question.
Sure. I'll let Phil answer if he knows that right off the bat, but to my knowledge, TW, I think that it's still not covered. It's not cost shared at this time, but I think that there's going to be increasing pressure, especially from the West, all these Western states, to try to get it moving. And, I think talking with people at the state level first, like Clint Evans and stuff, would be a great way to get going. And maybe that's an effort that CSU can work on. I know there's lots of groups right now trying to quantify salinity in the South Platte, and maybe that could be one of the goals of that project. I think that's good to bring up. But Phil, what are your thoughts?
No, I think that's well said. And the only thing I would add is just I think it'd be good to connect with your conservation district and get that person Casey connected with the Colorado Association of Conservation Districts to bring that as an issue to NRCS to explore.
Great. What was your second part?
The other part. Because of our soil type up here, I've long sought alternatives to commercial fertilizers because I'm just adding more salt as a result of those practices. And so what I'm always interested when I see these kind of talks and opportunity, what do we have coming forward in the technological realm, different kinds of technology that we're not adding, that we can use as fertilizer, but not adding salts. Is there anything on the horizon?
Yeah, I would say there are things on the horizon for managing salt, but they're not really focused on the chemical composition of the fertilizer, other than what I would comment on is maximizing efficiency in uptake, right? Because what really causes the salt problem is not necessarily the fertilizer itself, but it's the lack thereof the fertilizer going up into the plant. It's the stuff that doesn't go into the plant that becomes the issue. So if we can work on, and that's being actively worked on, is how do we make better fertilizer that goes all in the plant instead of sticking around and wasting into the soil? And that is a function of management as well. But I would say the genetics for nitrogen use efficiency, those kind of things really play a role there, as well as the fertilizer chemical composition, and then just making sure that producers are using the best management practices so that after they apply fertilizer, they don't just leach it right out afterward with an irrigation, right? So, or other things like that, timing it not right before a rain as possible. And I think those practices are pretty well followed. So I'd say the technology is more in the genetics and then the chemical composition of fertilizer itself to make sure it's up in the plant. But nothing magical yet.
Yeah, because in our native in these native hay meadows, the ability to genetically move these crops is I would assume somewhat limited. But was more thinking in terms of the microbiology in the soil that helps to be able to move this salt, and that was what I was interested in. And the last part of the question was I've been trying some commercially available. It's a sulfur 4 plus commercially available. It's kind of a immediate acting gypsum, which has for in my severe issues I've seen immediate season improvements, and that relates to the technology. If there are things coming along that we need to be aware of as producers.
Yeah, I'd be interested to talk more about that, TW. Maybe you can send me an email and we can talk about the gypsum stuff. But I just wanted to say that I work a lot in Mountain Meadow hay systems as well, including Steamboat and Gunnison and I-70 corridor areas. So I'm very familiar with it's not so easy to just say, yeah, change your genetics, right? Like it's and it's also our already low input system and options are limited and budgets are tight for fertilization already. So anything we can do in that area is better. But I do want to also just chime in before the next question and say, I think it's kind of a misnomer that people think that, this just, there's magical bacteria out there that make the salt go away, or at least make it better. To my knowledge, that's just, it's kind of it's one of those dangerous things about soil health that I want to at least, and if you have papers or other things to show me otherwise, great. But I'm going to say, to my knowledge, bacteria aren't really a solution for salt at all, other than if the bacteria are improving soil structure to make the drainage happen. The salt, it's not like they eat it and then it just goes away. The salt stays there. The salt is already in a pretty raw form. It's just 2 ions or whatever, right? So even if the bacteria eats one, it's still there. And if the bacteria dies, it's back in the system. So it doesn't make it go away. And in fact, the salt probably hurts beneficial bacteria, if anything. That's what it's showing, because then it's competing with the water that the bacteria need too. So, and salt, that's just what I want to say. There's no, to my knowledge, bacteria kind of solution to salinity and nor will that improving that help your salt problem. They're kind of two independent issues.
Great, thank you.
Yeah.
So the next question, AJ, is from Dick Perkini. What are good types of organic matter? And there is a lot of variability in the type of organic matter you can apply. You've got crop and forage residue, manure, compost, different types of like humic acid, fulvic acid, and whatnot. It doesn't matter if you're trying to combat salts?
Yeah. The only time it matters is once again if you're improving the soil structure and water holding capacity. So if you think that you're seeing better results with a humic acid compared to manure or compost, then use that. But I mean, I would say no. It doesn't really matter a whole lot. I would say your best practices, at least in row crop systems, are to make sure you're adopting like minimal tillage to maintain drainage pathways, right? Because conventional tillage and a lot of soil disturbance breaks any established water pathways that allow the salts to leach out quickly. So applying what you can and leaving the structure there, that's what we're looking at. I remember crop scouting back in the day, and it was like, humic acid was really popular. And then I was, as I became more and more in tune of what it was trying to do, it's like, yeah, it feeds bacteria, but what if your bacteria is like E. coli? Well, now you just made a bunch more E. coli. So be cautious with what you apply to your soil, and don't just think that it's just going to magically make it better, because a lot of this organic, depending on what you apply, uh, the organic matter might not stick around permanently. And so and it's really case by case and soil type based. So do get a consultant or somebody who knows the soil science well to make sure that you're applying something that will stick around and not just be a temporary boost.
So questions about leaching, and obviously that's something that you talked about a bit, but that issue of pushing those salts down, maybe just go into that a little bit more. And then Paul's question about, well, are there situations where you push it down and it comes back? I guess that would be more in a shallow water table that doesn't go away. But you got other situations where you're pushing those salts down beyond your root zone, but then that's going into shallow return flows and ending up being somebody else's problem, right?
Yeah, that's exactly it, Paul. So I think good question. But that's actually the whole name of the game. Like on a watershed level, the goal is to make every producer keep the salts out of the water table, but also out of the root zone. So keep it in this salt sandwich that's not really used soil. And yes, it is going to come back up and it's going to go back down after an irrigation. And it is going to come back up with ET and then it's going to go back down. Um, Juggling that is the magic number, because if you push it too far down, then it leaches back to the river and then it does become somebody else's problem, or to the groundwater table and somebody else is pumping it. That's what we see a lot in the Ogallala areas right now in the state, is just like they're so salty out of the groundwater because of that. Lots of leaching happening. So unfortunately, I wish it was as easy as just like, yeah, if you leach it, you're good. But you want to leach it enough to keep it out, but not too deep, because then it's somebody else's problem. So that's why it's such a tricky issue. And people have made careers off of that decision, or out of that question alone. So um, that's my short answer. But we could go into that deeper later if you need to.
So what about cover crops? We talked about organic matter a bit. If you are fallowing in the off season, you're growing a cash crop. Cover crops seems like maybe a good idea. You're shading the soil, keeping the soil cooler, so you should be reducing evaporative losses, but you have those roots that are growing, so you've got transpiration occurring. So is that kind of neutral, or cover crops beneficial to addressing salts and salinity?
Yeah, very good question. I think it's so much a it depends question, Phil. And I know cover crops are really popular, and they're also, one of the soil health principles as far as keeping living roots moving. And I would say um, it depends on how salty your water is, how salty your soil already is, um, and what kind of ET this cover crop that you have, how it compares to how much water you can irrigate. Because you really just need to figure out, if I can apply more, then, or if I'm going to get more water, then what's going to be taken away. That's the simple way, right? Because if the cover crop eats more water than you have, you're going to end up with more salt than you started with. But if you're able to irrigate a little more, and have some of that excess, then you're probably going to leach out a little bit, and that's going to be fine. But leaving the living roots in the ground, obviously, there's a lot of benefits to that because of the soil health implications, keeping those pathways there, and for drainage and also the root uptake. It's very good. But I would say, just be aware of that water consumption, because I think there's also a myth out there saying that cover crops will just always be beneficial. But what if my problem's water scarcity? Like, for example, once again, Northeast Colorado, the Akron area, if you are relying on winter moisture to have enough to plant in the spring for like a wheat fallow situation or a corn situation, the cover crop is going to eat more water than your snow is going to provide. I mean, that's what we find in northeastern Colorado. And so if your goal is to maximize soil water storage, planting a cover crop is probably not your best. And therefore, you would end up with more salt than you started with because this, let's say the snow adds 4 inches and the crop needs 6. That's 2 inches of water that you didn't have. And now there's more salts concentrated toward the surface that you have to deal with.
Okay, thanks, AJ. Any other questions?
Yeah, and the leaching, I didn't dive into that because it's kind of mathy. But if you do want to know how to calculate how much water to apply in excess of what the normal water is that you think you need to apply, it's the start is that Excel sheet. I'm gonna throw that back up really quick. But yeah, you can try that out. But there's also extension fact sheets, or you can reach out to me and I'll show you what that calculation looks like and send you the fact sheet. And that just tells you, that helps you get started. So let me know if you have any questions. You can always reach out. Yes, I can share the
question on the
slideshow.
slideshow, and we will also be posting this whole webinar as well. So we'll post AJ's slideshow on the agwaternetwork.org website, along with just the whole recording as well as the highlights. So you'll be able to access all of that, and we'll provide a link to that Excel spreadsheet too. Let's see. Do we have any other questions?
Mason, I think, does.
Yeah, I just have a quick question about gypsum. I've been seeing it more recently. I know California uses a ton of it for like sodic soils and things like that. What have you? I know you mentioned it, and you kind of mentioned that it's not like a panacea. It seems like some people think it is. Obviously, there's issues to it as well. What have you seen like with issues with adding gypsum just as a an all-encompassing solution?
Yeah, absolutely. So gypsum is, I think, because of the lack of knowledge around the chemical components of a saline versus a sodic soil, some people just think, I'm just going to add gypsum and it'll be all right. But what if the main soil or the main salts in your soil already are like calcium carbonate or gypsum or magnesium sulfate? Like adding gypsum isn't going to do a thing. In fact, you're just going to make your problem worse because now you're just adding a different type of salt. And so I think it's the lack of education around what to do with gypsum is the problem. But when you use it correctly, it's absolutely the best. It's one of the best ways to manage it. So if you know you have sodic and you know that SAR number that I talked about, and it says, you're mostly sodium, that's the gypsum makes a lot of positive impact for that because you not only are you getting rid of the sodium, but now you're creating soil structure because of the 2 charge on the calcium ion that gypsum has. So California, it makes a lot of sense because most of their salt comes from the ocean in various ways, whether that be through the air, the seawater, intrusion, groundwater, like whatever, right? So that's more likely to be seen. However, like TW mentioned, we're like a prehistoric bedrock. Most of Colorado is, right? And so the types of salts we encounter, although can be sodium, our bedrock and stuff, that's all shale. It's all like this kind of like calcium based carbonate or gypsum and other things. So you see a lot more. You don't want to add gypsum to a gypsiferous soil. So that's my caution. That's what I've experienced. Does that answer your question, Mason?
Yeah, no, that definitely does. And then I guess another part to that is do you see like in parts like California where it is like sodic soils, if we apply it too much that we're just pushing off and creating a new problem, or is that so far down the line it doesn't matter?
You can always apply gypsum in excess, and there are calculations to kind of estimate how many tons per acre you should apply. So I would always recommend checking those out. And if you need those kinds of materials to figure it out, I'd be happy to point you towards them. But you can apply it into excess and it just becomes a powdery residue. But I wouldn't say it would likely introduce a salt issue. It'd more likely introduce just like you're wasting your money because a lot of it would probably run off or just disappear. Because it doesn't have the capacity to hold on to that much powdered gypsum or whatever form that you put it on. So it's a pretty safe chemical. Rarely can you over apply it when you have a sodic soil, but I mean it's possible, but you're mostly just wasting your money.
Awesome. Thank you.
Yep.
Okay, well, thanks, AJ. Some great information shared. Really appreciate you taking the time to go through this with us. Salinity is and sodicity both are really big issues for us here in Colorado. And so I'm sure that folks can follow up with you. I doubt you would mind if they do. So if anybody wants to send your email to me, I'll be sure to forward that on to AJ. AJ, you might just real quickly throw your email address in the chat.
I will do. Let me do that really quick. Participants, more, chat. There we go. Yep.
So
feel free to email me.
yeah, and again, just really appreciate your time. This has been really informative. And with that, we're going to go ahead and wrap it up. Check back to the website next week, and we'll have this posted and have the highlights and AJ's presentation as well. So thank you for joining us today. Have a good afternoon.
You as well. Bye.